Okay. So in about a minute here, I'm just going to go through all of the most popular Facebook questions. Someone put together this list. I think it might just be in the last 6 months, but I think they might have also gone through the painstaking effort of filtering this to be the most popular questions of 2024. I don't really know. But it's probably a pretty good indicator of what Facebook is asking right now. Okay. All right, I think I've fiddled around with the technical stuff. I'm ready to begin. I gotta post this link in a couple places, but okay, given the root of a binary tree, return the vertical order traversal of its nodes values from top to bottom, column by column. Column by column, so it'll be 9, 315, 27. So I feel like the thing to do here is to use a hash map and just keep track of like, or like in Python, I would use like a default dict list and just keep track of like what column you're at currently. So I'd say something like, let's say return res at the end. And then we're going to have something that's like columns is going to be equal to a default dict list. Okay, and then I'm going to have some sort of like DFS function. And then I'm going to say something like DFS root. And this is going to fill up the columns, and that's going to be like a hash map. So that's going to be something like, here it'll be something like -1 is 9, and 0 is like 3 and 15, and so on. I actually think, I mean, I could either use a default dict of a sorted list in order to keep track of like what row I'm at, because I need the 3 to come before the 15, and here it will naturally do that. But you could imagine a situation where the 9 has other children and there's like a 17 below the 15 or right at the 15 or something like that. So I think actually the move is to not have a recursive function, but to do a level order traversal to fill this up. Yeah, which will always go top to bottom, left to right. So I'll say Q equals deck, and it's going to contain a root. Okay, and then I'll say like, I don't even think I need the depth really. I don't need to keep track of that. So I'll just say while Q, node equals Q dot pop for child in node dot left, node dot right. If child, so shorthand for if it doesn't equate to false, aka if it's not nothing. Q dot append left child. That's all we have to do there, I think. And then here we'll also say, I guess really we want to keep track of the like the x coordinate as well. So we'll say 0, comma root, and then here we'll say x minus whatever, x minus 1 child. So, and then I'll just change this to be like not a for loop. That was like too fancy. Okay. Nothing wrong with a little bit of copy pasting. But now we get to do this. I could have kept the for loop and I could have done some like for I comma child and enumerate and done some fancy math with like x plus whatever, but that's so much less readable than this is. And I think you quickly get to a point with fluency with this where readability is so much more important than actually being able to do the problem. Okay. Pop append left. Okay, and then we need to say something like calls at x dot append node. And then here we'll say x comma node equals q.pop. Okay. So now we have all the columns. And we can't just like, if we print the columns, it's not going to be in sorted order, sadly. Well, that's pretty, I guess we really need to say calls at x.append node.val. Yeah, so we can see 0 shows up first, and then -1, and then 1, and then 2. And these are in the right order, but these are not. So we need to, I think we don't even really need to define res. I think we could just say something like column.items, something like that. But I mean, we could also make it a sorted dict. No, I'm not going to do that because it's already a default dict that saves a lot of lines of code. So I think what I'll just do is like hand put it into a list. So I'll say something like, let's see. How do I want to do this? Or I could have res be, there's a couple ways I feel like you could do this a little fancy. You could have res be a dec and you could add to either side because you're always going to start at 0 and then be at 1 or -1 and then 1 and then 2 and then -2. And no matter how lopsided this is, you could add it in O of 1 to either side. I guess I'll do that because the alternative would be to sort it, which makes the time complexity for this whole thing go up to n log n. Whereas this would actually still be O of n, which is kind of cool. I bet a lot of people do this in n log n. So I'll do the O of n way just for fun. Okay, res is dec. So then we'll say like for x, or for id for x, because it's the x value, it's like which column it is. For x comma list, I guess, in calls.items. If res and x is less than res at 0. Fuck. Problem is that we need to keep track of the columns still. But that's okay. Like you still need to keep track of the column number. Because like say when we get to 1 or something, we don't know. Well, no, I was going to say like you would need to compare, is the current column we're adding going to be less than everything in the list or greater than? But I think if it's negative, it's always going to be added to the left. And if it's positive, it's always going to be added to the right. So we can just say if x is greater than or equal to 0, res.append L, else res.append left L. And then I don't even think it needs to be a list because it gets automatically casted, but that's probably good form because I don't think you really want to be returning a dec. That would be really weird. Oh, okay. None type has no attribute val. So I guess right here, I'll just say if root, do that. Else. No, not even if that is like 2. I'm just going to have the corner case specifically. If not root, return an empty list. Cool. All right, before I start the next one here, I'm going to paste the link to this. Return an empty list. Okay. Looks good. Okay, question number 2. And I think probably almost all of these I've done before. That's the nature of them. Minimum remove to make valid parentheses. Your task is to remove the minimum number of parentheses so that the resulting parentheses string is valid and return any valid string. Okay. So that the resulting parentheses string is valid. I see. So was going to say we can completely ignore the characters as far as the logic of the parentheses goes. And if I'm not mistaken, you really only would ever have to remove. I think it's really just going to come down to like the count. You could have something, I think worst case, or like the most cornery of corner cases could be something like this, where you actually have to remove like, there's two things you have to remove. There's all the parentheses that are that have nothing matched to the right of them, and then all the left-facing parentheses that have nothing matched to the left of them. So I think you kind of want to do two passes, one from the left and one from the right. Mark each of those as removed, and then go from there. So I think the first thing I'm going to do is say like s equals list s, so I can change it. So it's not, so like it's mutable now. And then in the end, I'm going to say something like return blank dot join C for C and S if C is not equal to, we'll say underscore. This is going to represent like it's been marked for deletion. So I guess if I pull up Excalidraw, like let's say S, yeah, let's like take this one. Oops. So here you have an extra, it looks like paren here. Otherwise it would be balanced. So I think what you would want to do to recognize that is traverse from left to right. You would say, cool, now we have one paren here. Now we have two. Now we're back to one because the first one's been matched. Now we're back to 0. And then here we're at -1. And the moment you're at -1, this can never be valid. So you would do that going right, and then you would do that going left. So I think there's going to kind of be two for loops here. For I, comma C and enumerate S. So I got to keep track of the index as well. A little, I guess, like how do you, if you deleted this, say, and then you had to go in the other direction, I don't think it would ever matter. Like, what I'm wondering about is like, if in one traversal, I start with this, and then I'm going to wind up with this. And then what if there was another traversal where now I'm starting with this like augmented thing? Do I want that? Or is that going to like mess something up if I have to like delete a paren? I don't think so. I think it's kind of just fine. Yeah. Here, I guess I have to say like, okay. So I guess I would say match C. So if C is and I'm going to have like current equals 0. So we'll say, okay, if C is an open paren, current, I'm going to say cur plus equals 1. Or else if it's this, cur minus equals 1. If cur is less than 0, then we say s at I equals an underscore. It's been marked for deletion. And cur is, again, 0, because this will never be anything below -1. So you can just say plus equals 1. But I guess this would be slightly faster and more explicit. So maybe that's the better thing to say. And then we don't even really need a case for the characters. Those can completely be skipped. Okay. And then it's going to be very similar here. And except it's swapped now, because now it's going in the other direction. And this feels like it could almost just work. Okay. So here what it's doing is it's saying, oh, I should probably reset cur. I imagine, yeah. That works here. I think as far as the underscores go, like this is kind of weird because the first parsing here, S is then changed. There's no longer these, and that could mess up the logic in the second loop. But I'm thinking about it, and I think it never can, because at the point where something's been marked for deletion, at the point where a left-facing paren has been marked for deletion, that kind of means that no right-facing parent to the left of it could be marked for deletion. So the logic kind of actually doesn't matter anymore. But that feels like it could be dangerous. If you had something like this, maybe not. Maybe it's okay. I guess it's good, because this, what happens? This gets, wait. Okay. If it's that, what happens? Because one of these gets marked for deletion. So it goes. This gets marked for deletion. And then, yeah, I guess that logic makes sense. I'm still a little bit skeptical, but cool. Okay. 2 down. I'll just power through a third. Okay, range sum of BST. Let's get rid of that. Return the sum of the values of all nodes with the value of the inclusive range low and high. Yeah, my immediate instinct is to try to do a one-liner just to be funny or something, I guess. But if I was not doing that, I think what I would say is like return DFS root def DFS node. If not node, return 0. Res equals node.val times low, the inclusive range. So less than or equal to node.val is less than or equal to high. Res plus equals DFS of node.left. Cool. So here there's like slight kind of a mathy little trick going on. Where it's like, this is shorthand for if node.val is greater than low and less than or equal to high, greater than or equal to low, then add node.val to res, which would otherwise be 0. And the advantage of like doing this is not only do you get to feel kind of fun and mathy, it's also called branchless programming. So like the fact that you don't include an if statement means that most computers, they don't have to think about the fact that like there's 2 things it might have to compute because there's an if statement. It will just like do both things anyway, and that allows the computer to like compute ahead of time much more efficiently than if you had an if statement. Okay, I want to put up a little number here that says that like I've done 3 or something. Okay, put up a text. I'll say problems done 3. Okay, a little big, but let's see. No, that's not even worth it. Okay, valid word abbreviation. String can be abbreviated by replacing any number of non-adjacent, non-empty substrings with their lengths. Given a string and an abbreviation, return whether the string matches the given abbreviation. Okay. So I guess you would just kind of keep an index in the word, and then you would do the appropriate thing in the abbreviation. Although, okay, the links should not have leading zeros. It doesn't say other than the number 0 itself, which it often will say. Well, it does say any number of non-empty substrings with their lengths. I guess I'm wondering for like 12, could this represent a 3-character word? Yeah, no, it can't. because right here it says this is not valid. And zeros don't work. Okay, so the fact that you must have all adjacent digits correspond to the same number, I think makes this a little bit simpler. So I guess I'll say like, I'll have like a digit cache. Yeah. And then I'll say, we'll have the index in word itself. And then for I in abbreviation, I don't even think I need I think I can say for C in abbreviation. If C dot is digit, cache dot append C. Cool. Okay. Else, I'm gonna do that just because I don't. It's slightly less indentation going on. Okay. If cache, then you got to do something. Then you say idx plus equals. We're gonna do that, and then we're also gonna say cache dot clear. idx plus equals int empty string dot join cache. So we're saying turn the cache into a big number. idx plus equals that. Okay. And I'm gonna have to do this like after the loop in case the cache has stuff, in case it ends with a number and not a character. Do that. Okay. If idx is greater than or equal to the length of word, then you've gone too far, and then you can immediately return false. Or else, if word at idx is not equal to abbreviation, or is not equal to C, return false, and then idx plus equals 1, because you now have traversed that single character. And then in the end, this has to happen again. Oops. Okay. This is my first kind of suspect for something that's messing stuff up. No, it's 12 and 4. That makes sense. So I guess what I'll do is I'll say like print C and word from idx on. Okay, that's right. So it makes it up to the I and then it skips that. So Z Asian, and then N is nation, but the cache has 4. Oops. Okay, so then it's just an N. Wait, let me think about this. Okay, that indentation is whack. We have the N and the N. Okay, idx plus equals 1. Oh, right here it should be exactly the length of word. So I guess if idx is greater than the length of word, because you could have a world where, yeah. Okay, I kind of believe in this. A's, oh, the leading zeros. Let's see. So right here we would say if cache at 0 equals 0, return false. It's because that's happening also at the end here. I and 1. Oh, okay. I guess you have to say return IDX equals length of word. Okay. Let's keep it going, I guess. Valid Palindrome II. Given a string S, let's skip that. Return true if S can be a palindrome after deleting at most one character from it. Okay. Let's see. So string hashing is my very first instinct. If I'm trying to not do that, let's see. If you remove any one character, it can be a palindrome. That's true. You can remove the B. This is true because you could remove the B or the C. Okay. And the constraints are like not easy here. Okay, A, B, C, that's false. So I guess if you have a string, there's kind of always two comparisons you'd want to make. Like there's comparing these two A's together, you would always want to do. Or like, I feel like if there's a bigger string, like RR, R, A, B, A, R, something like that. And then we separate these out. So like, if you remove the B, I don't even think that really changes any of the, no, that does change the comparisons. If you removed this A, I'm just going to do string hashing. I don't want to think about this too hard. Which means copy pasting my beautiful string hashing piece of code. Let's get rid of that. Oops. Let's see. I want to make sure this isn't like some work in progress thing. Yeah, this looks good. So the first thing I have to do is say S equals int or ord C for C and S. Okay, and then you're kind of comparing like every. Is that even that simple? I think you can do this in just like dynamic programming. I think you can say def DFS. So we're going to have the index and whether you've skipped. And then we're going to return something like DFS of 0 and 0 you haven't skipped. And you can't have I and J. You can't have like the starting index and the final index. I guess you, but there's kind of, there is two options every step of the way. There's either you skip the left character or you skip the right character. But I think we could incorporate that into skipped and say, like skipped actually isn't a Boolean value. Skipped could be 1 or -1, and -1 represents skipping the end character rather than the beginning character. Because you only have, if you only have to do that once, you don't really need I and J as the state space. And I don't even think the cache is really necessary, but whatever. Just include it out of habit. So if skipped j equals, let's see, so if you haven't skipped anything, it would be j equals n minus 1 minus I. Because like if I is 0, you want j to be n minus 1. If I is 1, you want it to be n minus 2. So then, but then also minus I plus skipped. It's going to be something like that. Let's see, if skipped is -1, if skipped is -1, then we'll just say j minus equals 1. Yeah, if skipped is 1, then I guess I plus equals 1. I think this might have some serious issues, but whatever. No, I think I'm severely overthinking this. I think skipped can totally be a Boolean. No, you have to rethink j every time. Well, maybe maybe you could have I and j. Because the state space then is O of n squared. But I don't think you would ever explore the full state space. Like if you had just any old random string, you would try skipping every step of the way, but you would probably run into errors. But you could, yeah, okay, we'll have I, j, and skipped. And then this is no longer really a cached thing. Okay, if s at I doesn't equal s at j, return 0. Yeah, if I is greater than or equal to j, return 1. Okay. And then I'll say res equals 0. Return res. Return DFS of I minus 1, j plus 1. I don't think there's ever a world where you want to skip if you're at the same character. Like if both of these are A, now you could, like here, if this was AABA or something like that, AABCBA, you would want to skip an A. No, because you could always just skip later when they're not equal. So I don't think there's ever a world where you ever want to skip when the characters are equal. Okay, if not skipped. So if you haven't skipped yet, then try to do that. So say res or equals DFS of I plus 1, j minus 2. I don't think that's necessary. I, j minus 1, 1. So you're saying try skipping j or try skipping I. Okay, and then return res. Oops. Oh. And I don't think this can, I think the time complexity of this is just still linear because this choice would be O of 2 to the n, but this can only happen once before skipped is turned to true. So I think this is fine. Not the fastest, but I guess that's what you get with recursion. return the lowest common ancestor. Okay. And each node has a... What the hell is lowest common ancestor of binary tree 2 and 1? This seems like the most bare bones version of this question. Oh well. So you could do binary lifting. That would be the appropriate approach, but I'm not going to do that because that's like a whole thing, and I don't really want to bother with that right now. That's how you find the least common ancestor in like O of log n. But in order to even do that, you would have to... Oh, I guess it's 2 nodes of a binary tree and you're not given the root. Maybe that's the twist. In order to like binary lift, you have to like kind of parse the whole tree to begin with. So it's already like n log n to do that. So that's a lot of overhead that I don't think is really worth displaying right now. Okay. Well, I guess scene equals set. While p is not none, scene.add p.val, p equals p.parent. Okay. And then while q is not none, if q in scene, return q.val, q equals q.parent. And then this should never show up. I have to imagine they're like in the same tree. I can't imagine they'll like just be part of different trees. If q.val in scene. Return string. Oh, do I have to return the node? Each node will have a reference. Yeah, okay, that's fine. This becomes a dictionary. Yeah, imagine this is really slow because the faster things will... No, I don't even think it's faster to do binary lifting. Simple enough, I guess. Oh boy, basic calculator 2. Integer division to truncate towards 0. Damn. Here we go. S equals list S. Okay. Eval. Okay, it says truncate towards 0. So I think actually this is going to have problems because you could divide a negative number. Like I think if it was like, let's see. We have 3 plus 5 over 2. Yeah, okay. So the spaces just don't even matter. If we had like 3 minus, is that? Yeah. So this should be 3 minus 5 halves, which will evaluate to 2. So it should be 1, but it might return 0. Nope. All right, well, if this just works and it doesn't raise any questions that I'm doing explicitly what it says not to do, then I'm going to call that a W because I do not want to do basic calculator right now. Oh, Jesus. Good thing I skipped that last one because this is a nightmare question. You're given a nested list. Each element is either an integer or a list. The depth of an integer is the number of lists that it is inside of. Turn the sum of each integer multiplied by its depth. 1 indexed. Okay, and we have get list, get integer, set integer, add, hold is integer. Okay. I guess. The problem is you would think to do this recursively. You would think to go like, oh, okay, so for a given, nested list, like look at all of its, if it's an integer, return that, or else look at all of its elements and like add those. But the problem is that those are going to have a random depth. And if you're at that depth -1, then like somewhere along the way, you're going to have to be like, multiply this by 6/5 and that kind of thing. You'd quickly get into float arithmetic. It would get really ugly. So instead, I think a stack is the appropriate thing. So stack equals, because then you can keep track of the depth as well. Or, you know, I think I guess you could just do this recursively and keep track of the depth as well. I'll do that. No, I'll do a stack. That's a little nicer. So we'll say 1 nested list. No, I'll do recursive. So we'll say depth L for list, or R. R dot is integer. Return R dot get integer times depth. Else, if it's not an integer, then it has to be a nested list. Else, get list returns a list. So for element in R dot get list, res equals 0, res plus equals DFS depth +1, element return res. Yeah. And just for the sake of like syntactical consistency, I'll do that. Return DFS 1 nested list. List object has no attribute in integer. Oh, it's a list of nested integers. That seems really needless. Man, I was like, this problem seemed a little too easy to be true. I guess that's what makes this problem really nightmarish, is that you have this weird custom nested list class that has no real purpose and is like, in my mind, the pinnacle of like someone created a random custom class that's like this shell that's gonna, it's like the ultimate nightmare of Python programming that someone gave to you and you have to debug. And not only that, but also the object that you're given isn't even a nested integer that's a list of other nested integers. It's a list of nested integers, like the built-in list, not the nested integer list. very interesting problem. I guess they probably have this to be like, can you debug an intern's code? All right, number 10. Random pick with weight. I'm going to go ahead and let my eyes glaze over here. Discovers the weight of the ith index. You need to implement a function which randomly picks an index in the range of that. Okay, my immediate instinct, and this is probably just that I am remembering / my eyes did register something right there, is to like do a prefix sum. So if we have like, this is a weird test case. The only option is one thing, so whatever. But here, there's a 1 in 4 chance we choose this, and a 3 in 4 chance we choose this. So if you had like a prefix sum, then you could do like a binary search kind of, and be like, choose a random number from 0 to the sum of everything. Like what interval does that number land in? Pref equals list accumulate W. Okay, pick index, return. I'm gonna try and do this all in one. Return self.pref.bisect left random.randint 0 self.pref at -1 +1. I don't remember if that's oops. I got sorted lists on the brain. I don't remember if this is +1. Oh, what am I doing? Print randint 0 1. So we'll see if this includes 1 or if it's like exclusive of the upper bound. It does include 1. So I think that means that we don't want the plus there. So this means it's going to choose any number between 0 and 4. So if it chooses a 0 or a 1, then it will be this. So that's a 2 chance. And if it chooses a 2, a 3, or a 4, then it will be the 3. So I think actually we want bisect right, so that if a 1 is chosen, it will pick the 3, and if a 0 is chosen, it will pick the 1. So that means that if there's a 1 or like a 2 or whatever, then there's X amount of options below that. That makes sense. And then I think it's self.pref at -1 -1. So it's bisect left anywhere between 0 and 3. I'm gonna go with that. Nice. Looks good. Kth largest element in an array. This one's kind of a classic. So what they want you to do is go through with a heap and say like, if k is 2, can you solve it without sorting? Yes, by using a heap. So they want you to go through with a heap, and like I think everybody's first instinct is to have a max heap. So you say something like heap is this for x in nums, do something, and then return h at 0. And then we'll say like h dot or heap push h x if length of h is greater than k, heap pop h. So this is what they want you to, or this is like, I think everybody's first instinct, and this does pass, but there's, or wait, no. Yeah, this is the efficient way. This is the right way to do it. But there's kind of something going on here where this is a min heap and you're finding the kth largest element by constantly looking at the minimum thing in the heap. And actually, I think what most people's first instinct is to do is to say, well, really, I want a max heap. So I'll say like heap push h -x. So I'm like keeping track of the largest elements and then do some, but It's the difference. If you use a max heap, even if that seems like it makes sense because you're finding the largest element, the kth largest element, that actually requires you to do this in O of log n time, like n log n time, as opposed to this using a min heap, which allows you to do it in O of n log k time. And k will always be smaller or equal to n. Okay, oh, this one's kind of fun. Implement a power function which calculates x raised to the power of n. So, and n can be gigantic. So this problem actually is like, lives up to its status as not an easy question, despite being an extremely short description. So what they want you to do here is binary exponentiation, which is like a really efficient way to calculate the power of a number. So if you just said like return x dot, or what would it be, pow xn, they might have some built-in thing that's like, you should not do that. I wonder if they do. No, they don't. Okay, so I guess that's how that works. But if you wanted to implement this on your own, which is the point, you can't just say for blank in range n res times equals x, return res. You can't do this. Well, that has its own issues. But negative numbers aside, even if there were no negative numbers, if this was like, let's say 1.00001 to the like 10 millionth, this probably won't, okay, well, I guess the fun part here then that they're intending for is the like negative thing. I think the way around that is pretty simple. It's just like if n is less than 0, or I'll say negative equals 1. I'll call this polarity. Is -1 if n is less than 0, else 1. And then we'll sort of normalize n across, like we'll make sure it's positive by saying n times equals polarity. And then here we'll say res if polarity is greater than 0, else 1 over res. That should be fine for that. Yeah, so this kind of handles negative powers now. Maybe it's just fine. I mean, maybe this will just pass. Maybe the challenge here that they're intending is that like, oh, what do you do if n is negative? Gotcha. Which is kind of interesting, I guess. But I thought what it was going to be is more something like if you had 1.0000001 to the power of, again, 10 million. Or yeah, like just literally 1 to the power of 10 million. Like this took almost 4 seconds. If I don't even have that, if I just had 1 to the power of, again, like this is going to get a TLE. It doesn't really matter. But the point is that if n is humongous, you can't get away with just having a range up to n. And they specifically say n can be gigantic. So what you do in that case is binary exponentiation. And the idea behind binary exponentiation is like, I think it's worth writing it out. So if you have like, let's say x is 1. Let's ignore that right now. Or let's say x is 2, just for the fun of it. And then let's say n is like 100. So you could loop through 100 times and say like 2 times 2 times 2 times 2 times 2, 100 times. Or what you could do is you could say, well, what is like, let's multiply 2 by like 4 and by 8 and by 16 and these other different powers of 2. That's really like 2 to the 4th and 2 to 2 cubed and so on. And 4 is like 2 squared, whatever. And then we're going to do that a certain number of times. So now instead of like here, we have to add up 100 2s in our equation. We have to write out 2 100 times. Here, we would have to write out 2 once, potentially, 4 once, which is going to be like 2 2s, 8 once, which is going to be like the equivalent to 3 2s, 16 once. Actually we wouldn't need the 8 for reasons I'll explain in a moment, but now it's sort of like we, instead of having to write out n 2s, we would have to write out like log n 2s. And the idea is that we're kind of breaking down n to be like, what is this in binary? So for example, if n was 1, then that's a single 2. If n was 2, then that's going to be a single 4. If n is 3, then that's 2 times 4. If n is 4, then that's 16. And so on. And what we can kind of recognize is like, we can break n into its binary, and then use that to find, and we know, sorry, I should say like 16, we can calculate this way faster than 2 times 2 times 2 times 2, because we can say, well, that's going to be 2 times 2, and then that times itself again. So like if x is 2 times 2, then it's that times itself. And for 32, that's not going to take a bunch of, that's not going to take like 8 multiples of 2. That's just going to be like x is 2 times 2, and then x is x times x, and then x is x times x. So we're sort of taking advantage of the fact that we can just like square to get the next largest thing really quickly. And it might make more it might just make more sense if like we go back to n equals 100, and say, okay, what's 100 in binary? Okay, so 100 in binary is this random thing. So it looks like it's saying it's 8 plus 32 plus 64. No, I'm sorry, 4 plus 32 plus 64, which makes sense. So we have kind of like 3 things here. We have 4 plus 32 plus 64. So another way to write 2 to the 100 is really 2 to the 4 times 2 to the 32 times 2 to the 64. And now if we can find a way to write each of these expressions in less than like 64 terms, then we found a way to calculate 2 to the 100 much more quickly than a loop iterating 100 times. And like 2 to the 4 is just going to be 2 times 2. And then 2 to the 32 is going to be like, again, 2 times 2 is 2 to the 4. So then times itself, we'll call it x, is going to be 2 to the 8th. Yeah. And then times itself again is going to be 2 to the 16th. And then times itself again is going to be 2 to the 32. So this only needs to calculate 5 operations. And then 2 to the 64 is just going to be that times itself again. Because like 2 to the 32 times 2 to the 32 is 2 to the 64. So the idea is you parse through the binary and you kind of go like, what if we had no 2s? What if we had a single 2? What if we had a 4? What if we had an 8? What if we had a 16? What if we had a 32, and so on? And if x was 3, it's exactly the same thing. It's just like powers of 2 of 3. So this would be like 3 times 3, and then 3 times 3 times itself, times itself, times itself, and then 3 times 3, whatever. There we go. Yeah. That's kind of what you would want to do. So we'll say something like n equals bin n from 2 on. Or really, I think we would want to say like up to 1 counting backwards. So now we have like, that's really confusing. So this is like the binary representation of n. So then we can say for bit in n, if int bit, so if it's a 1, then we'll say like res times equals current. We need a current too that we're going to kind of recursively multiply by itself. And here we'll say like current times equals current. There's going to be some workshopping here, but whatever. Yeah. Cur equals 0. No, wait, cur equals x. There's going to be some off by 1 stuff. Because you want to start out current, the 0th bit is going to represent the 1's place here. So for example, 100, this is going to be like times, no, yeah, wait, this is 2. Whatever. I'll submit it and it'll probably be obvious what the off by 1 error is. Okay. Let's see, 85. Okay, so I think, yeah, okay. So this is backwards currently. So it's saying for bit in n, but this is most significant to least significant. So I think I am going to say like that, counting backwards to 1. So now this should be, let's see. Oops. Wait, really? Okay, yeah, so I think now the issue is that I'm overshooting significantly. $256. Okay, that's more sensible. So this is saying if you have 10, n to the power of 2 to the power of 10, we're saying there should be, that's not right. Let me look at this again. No, wait, no, this is right. I'm an idiot. So 10 equates to 1010. So we're saying look at the 0, look at the 0th. Let's say that for readability. Look at the 0th bit, that represents, is there a single 2? Okay, yeah, that's the issue. It's that cur times equals cur should be at the end. Is there a single 2? Is there a squared 2? Is there a 4th power 2? And so on. So now these numbers can be whatever we want. That could be like some giant thing. And if it's like 1 to the power of that, then it should be pretty simple. You could probably also be like, if a number is, if it's 1 to the power of something, just return 1. Otherwise, for blank in range n, multiply it by itself. That would probably work too. This definitely shouldn't TLE. So I'm surprised that this is taking a while. I would expect a wrong answer, but I wouldn't expect a TLE. Maybe LeetCode's just slow right now. There we go. Yeah, this is binary exponentiation. It's pretty cool. And you can, like, it works for exponentiation, but it works for other things too. So you can do this. Earlier I mentioned binary lifting is kind of another version of this, where you break a number into its binary representation, and that actually gives you a lot of useful information in these ways that you wouldn't think. Another one is like matrix multiplication. You can multiply a matrix by itself like a billion times, and you can do that in like 20 operations. 25, I guess. Dot product of two sparse vectors. Interesting. So they're mostly zeros. Okay, so I guess you can't just directly take the dot product over and over again. Because if you're going to do that, like 100 times, that's O of n 100 times. I'm assuming you could do that on the order of n times. So you got to think of a more efficient way. I guess my first thought is you store the indices. So you turn these into like, I guess, dictionaries or something. And you say, or I think you could just do two lists and you could say, okay, this does have something at index 0. And then these you just completely skip. And then you say, and now the next thing is at index 2. So you only have to parse through n once when you initialize. And then this would say, this has something at index 1, and then it has something at index 2. And then here you would just have like two iterators that would just go over. That makes sense to me. Oh, interesting. This is actually kind of an interestingly phrased LeetCode problem, because normally it's like all encompassed, but here you're actually going to initialize two objects. So you're saying return the dot product of two sparse vectors. So you're returning it's going to be self dot product with the other one that you also initialized. Okay, yeah. So I guess self dot r equals, I think you could do this really efficiently. I think you could say I comma x, or I x in enumerate nums if x. And then here we'll just return 0 right now. Oops. Okay, 0, 1, 3, 2, 4, 3 looks good. Yeah, so at index 3, they both have something. I'm wondering if there's like I feel like there's got to be some really clever way you could just do this really elegantly, as opposed to saying something like j, like I, j equals 0, 0. Yeah, what would you do? My mind's kind of spacing out. So here you would want to say, I guess you only really need one. You could say idx equals 0 for I in range length r. I'm going to say r equals self.r. This isn't just like for ease of use. This does help very slightly. If I didn't have this and every single time I said self.r, actually that would be fine. But if I said something like up here, g equals 9.81, and then here I was like referencing g over and over again, that's like, it's not super efficient, because what would happen is like, this would look in the local scope, and then it would look in a larger scope, and then it would look in a larger scope, and like looking through those scopes over and over again is exactly the kind of thing that makes Python be a lot slower than other languages, because it doesn't want to just tell you, hey, define that here. Don't keep making me look in outer scopes over and over again. But that's pretty tangential. So r is self.r for I in range length r. I guess I'll say while idx is less than length of, and I'll also say like other equals vec.r, or I'll say r2 and r1. While idx is less than length of r2 and r2 at idx at 0 is less than r1 at idx at 0. So we're saying like, look through all the zeros of the other thing until you get to something that's greater than or equal to where you're at now. IDX plus equals 1. If IDX is less than length of R2 and R1 at I, oops, this should be at I at 0. At 1, no, at 0 equals R2 at IDX at 0. So now, like, if there are two things that are actually at the same coordinate, so here these are at the same, here we would have like two things that are at 3, then I guess we say res plus equals R at I at 1 times R1 at IDX at 1. No, R1 and R2. And then we say return res. And it's like the sum of everything multiplied together. Cool. It says follow up. What if only one of them was sparse? If only one of them was sparse, I guess what I would do if I'm thinking like off the dome, oops, I just have a print statement in there, is I would probably have some sort of is sparse determination in the initializer. And if it is sparse, then I do this. And if it's not sparse, then I have it be normal. And then anytime you take the dot product, you would check like, are one or both of these sparse? If so, there'd be a slightly different piece of logic. But honestly, I think even, I guess if something isn't sparse, like if every single thing doesn't have a 0, for example, this is a little redundant, but I don't even think it would be that much slower. I think this would just be fine for that too. Okay, buildings with an ocean view. I've not done this one. There are n buildings in a line. The ocean is to the right of all the buildings. The building has an ocean view if the building can see the ocean without obstructions. Okay. This seems very much like a monotonic stack problem. Yeah. I think what I would say is like, if you have all these built, let's say like we have some array, and what that corresponds to is like this, 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 that, and that. I think what you could say is like, go backwards, because we're looking to the right. For every single step, like either add it to the stack, like pop everything off from the stack that is smaller than it. So here we wouldn't do anything, and then add it to the stack. So let's say that's building 0, 1, 2, 3, 4, 5. That's building 5. So the stack would be 5. We would move here. We would say pop everything off from the stack that's smaller than it, which is nothing, and then add it to the stack. 4. And the fact that the stack, like the fact that it didn't pop everything off the stack means that like this doesn't have an ocean view, but this one does. It's the rightmost, so it always will. But more importantly here, like it popped everything off of the stack. So then when we go to building 3, it would be like pop everything off of the stack that's smaller than this, which is everything, and then add it to the stack. I think you could probably optimize by not adding stuff to the stack if it, I don't even think you need a monotonic stack, honestly. I think you can just take like a rolling, turn a list of indices. I think you can just take a rolling maximum and just be like, is this the current maximum? Yes, no, yes, no, yes, yes. I think that's all you have to do. So we'll say MSF equals negative infinity, just in case there's a bunker to the right that has a weird cliffside view peeking out of the cliff or something. For h in heights backwards, if h is greater than okay, yeah, they have to have a strictly smaller height. So if h is greater than MSF, MSF equals h res dot append h, and then it wants it sorted in increasing order. Oh, and it wants the indices. So I guess really I should say for I comma h, in heights -1, and then this is going to be like n minus 1 minus I to get it to be like the index is now left to right and the building's values are now right to left. And then sorted in increasing order. It's talking about the indices, so it wants the wait. Oh, oh yeah, no, yeah, okay. It just wants the indices in increasing order. So this should do that. This will add the indices sorted in decreasing order. So I think all we have to do is just say return res backwards. Yeah, a lot of monotonic stack problems I feel like kind of boil down to greedy problems. This feels like a common occurrence. The ones that can't boil down to greedy problems are a lot trickier, I find. Okay, lowest common ancestor. Wasn't this just the last question? Given a binary tree, find the lowest common ancestor of 2 given nodes in a tree. Oh. Okay, so lowest common ancestor of a tree, of a binary tree 3 gives you the parent. This one doesn't give you the parent. Okay, well, I guess it's going to be the exact same code as the question I just did, but you just go through and give everything a parent. That feels a little like cheating, but whatever. In fact, I'll not do the bad coding practice way. I think the bad coding practice way is something that's going to be like def will prime the tree, or I'll say, yeah, that's fine. Prime the tree. Or I can even just call this DFS. Node parent. So we'll say node.par equals parent for child in node.left, node.right, DFS child. And then at the top we say if not node, return, I guess. Okay, and then if we say like print p dot parent, and we want the root to have no parent. So if we say print p dot parent, it should print whatever p's parent is, or p dot par. So this is kind of like, I feel like the quick and dirty way to just quickly give everything a parent. So it looks like its parent has a value of 3 here. So p is 5. 5's parent does indeed have a value of 3. But the problem is now you've like edited your code. So if this is in some other bigger code base, you just added a bunch of random variables. Like you just changed around these random classes to have something that like maybe a tree node isn't meant to have a parent. Maybe someday it'll have a parent and that'll like have a different meaning. And you've just sort of predicated your code on erasing over and changing these things about something that might want to be considered immutable. You've like changed the state of the thing that's being inputted to you. So instead of that, you could just have like a parent dictionary. And I assume all the values have to be unique, yeah. And even if they couldn't, for some reason, tree node in LeetCode is hashable. But anyway, you could just say parent at node equals pair. And then now we can just say like print parent at p. Yeah, and it's still like some node with a value of 3. Okay, so now that every node has a parent, again, like you really could just do binary lifting. And this is the kind of thing where if in an interview they gave you this question, you would really want to bring that up and you would probably want to implement it and say, I know a faster way, binary lifting, that allows you to do this in logarithmic time as opposed to linear time. But the thing about binary lifting is that you have to, just like giving everything a parent, with binary lifting, you have to like give everything a list of ancestors that's like log n length potentially. So that would be n log n of sorts, to give everything a list of ancestors. So that would actually increase the time complexity, even though that would decrease the time complexity of the actual thing you're trying to do. So binary lifting is really useful if you have like a series of queries that you're doing in a tree. Then that's really valuable. But in this situation, laziness and also the nominal increased time complexity drives me to say that that's not really worth doing. So instead, I think I'm literally, not only am I not even going to do that, I think I'm also going to find the code that I just wrote and just kind of copy paste that. Because I don't really feel like typing this out again. So we have a scene dictionary. Yeah, and we're just saying like trace up through all the parents from one node, add them all to this dictionary, trace up through all the parents of the other node. If you see anything in a dictionary, that means that that's the first parent that you've seen. Yeah, so we just have to say P equals parent at P and Q equals parent at Q instead of Q dot parent. And the idea behind binary lifting is like you keep track for every node of its immediate parent and also like its grandparent and its great 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 grandparent, and then its great 8 times grandparent, and then its great 16 times grandparent. So it's sort of like you're keeping track of all of the powers of 2 ancestors that a node will have. And then that allows you to kind of say, like, from P and Q, you look at their parents, their ancestors directory, and you say, like, at what point you binary search through that. So you say, like, at what point are their ancestors the same? That means that the great, 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 whatever grandparent is, like, at or below that point. And then at what point are their ancestors different? Because that means that the lowest common ancestor is above that point. So you binary search anywhere between the root and I guess like one of the 2 nodes. Okay, that was 15. That's a pretty good time. I've been streaming for 1 hour and 22 minutes. So 15 problems. I guess that's like what, 6 minutes a problem, something like that. Okay, merge sorted array. Oh. Final sorted array should not be returned by the function, but instead stored inside the array nums1. I see. Okay. They clearly want you to do this in O of 1 space. Because I feel like you could kind of just have two pointers, like I and J, and count up, make a new array, and then just set nums1 to equal to that. But I think that probably wouldn't even work if you did that. If you said like while I is less than M and J is less than N. If nums1 at I is less than nums2 at J, res dot append nums1 at I. So I think this wouldn't work, and it's kind of for a specific memory reason that they're able to detect this. If you just said return res, or if you just said nums1 equals res. Yeah, I think it's going to have problems, even though you're giving... Let's see. This should be 122356 is what this should return. While I is less than M and J is less than N, or J is less than N, and then we say if J equals N or that. Oops. me think about the cascading if statements here. So, we can just have like if I equals M, then it's this. If J equals N, then it's this. Or else you actually have to compare them. So now this is like giving what we want it to give, and we set nums1 to that. But what we're doing here is we're saying now nums1 refers to this array. But at least in Python, the issue is like we're only setting this in the local scope. So whatever void function merge is supposed to be, whatever's supposed to be calling merge, it's going to like create the correct answer, but it's not actually setting that original array to be this. So I think what you could do is you could say nums1 at nothing, like actually fill up nums1 with res. And then that works. This is still O of n space, so it's like clearly not what they want you to do, but this does get around LeetCode's like checking of this as a void function, which I think is like a cooler accomplishment than actually doing this in O of 1 space, because doing this in O of 1 space is like such LeetCode interview core. That's such a useless thing to be able to do in my mind. But I think what you would do is you would still keep 2 pointers, and then you would say like you would keep 3 pointers, and you would say as you go, keep track not only of where you are in nums1 and where you are in nums2, but where the first 0 is in nums1, and then you would be writing to that as you go. Yeah, and there would be a lot of like shifting nums1 at I to nums1 at IDX or something like that. Okay, simplify path. It's an absolute string. Oh boy. A lot of these weird string questions. It starts with a slash. Any 2 directories are separated by a slash. It doesn't end in a slash. And it doesn't have any double periods. Any other format of periods such as that are treated as file/directory names. Okay. Going 1 level up from the root directory is a no-op, as the root level is the highest level you can go. Yeah, this definitely feels like a do you understand Linux more than like a DSA question, which I'm not super wowed about. So I guess what I would do is I would say, I guess the first thing is detect any 2 slashes and turn them into 1 slash. So if you had like home slash ... slash test, I guess it would return slash test. Path equals path dot split slash. And then I think you could just say like x for x in path dot split slash if x. And then this should get rid of double slashes and the ending slash. So you've gotten rid of that. You just have the dot. Here, yeah, now the double slash, this was previously like, and also have an extra empty item. Okay. And then I guess we'll just say like res equals nothing for x in path. Res If x equals dot continue, I guess that just means don't do anything, or match x, case dot continue, I guess. Might be a better way to phrase that, but whatever. Case dot pass, no. Case dot dot, if res dot pop. Okay, and then for anything else, that means it's a directory name. So say res dot append slash plus x. I wonder if you could just say slash dot join res. No. Seems like the kind of problem where you just go for it and run into whatever issue. Or you don't run into any issues. I'm going to try to make it to 25. But first I'm going to go pee real quick. Subarray sum equals k. Return the total number of subarrays whose sum equals k. Okay, yeah, this is like a prefix array problem. You either take a prefix array or you just do a rolling sum. I actually don't even think you need a prefix array, but it doesn't really matter. Because it'll be O of 1 or O of n space anyway. So I'll say like make a prefix. So now we have this prefix. This should be 1, 2, 3. Cool. And then we'll also have a counter. And then I'll say something like for x in pref. So look through every prefix. If x minus k, I don't even think we need to say that. I think we can just say res plus equals c at x minus k. So this is like, look at all the occurrences of x minus k that there have been. And then c at x plus equals 1. Okay, 1 expected 2. Oh, it's because we need to say c at 0 plus equals 1. Like if we run into the subarray that has a sum of 2, we've run into this prefix at 2, but there's no instances of 0, even though we have the empty set in our counter. That's just like, but what about that and not anything? Like what about that alone? And I think to do this faster, you could do this like not with a prefix sum. I think you would just hand keep track of what the current prefix is, because you're never actually referencing pref at anything other than x. So you would just be like, look at the current rolling sum. But that's a little bit quicker and faster, I guess, to type out. Find peak element. Again, I think I've done pretty much all these questions. Peak element is strictly greater than its neighbors. Write an algorithm that runs in O of log n time. So this is definitely a binary search question. I think the idea is you binary search using, instead of the predicate being like, are you greater than or less than the element you're looking for? The predicate is like, are you in a decreasing portion or are you in an increasing portion? Or like a decreasing portion or a non-decreasing portion? Can the answer ever not exist? Nums at I doesn't equal nums at I plus 1. That tells me no. I don't think. Because if there can never be two equal things, then there's always a local maximum. It's and if all of these are strictly ascending or descending, then it's going to be like at the beginning or the end. So I guess I would say L and R is equal to 0. This is my like binary search template. L and R is going to be equal to 0 and N. And then I'm going to look for the greatest element that is... Wait, I did not read this problem very closely. Given a zero index integer array nums, find a peak element and return its index. Oh, okay, so it's not like a mountain array or anything. The O then solution is obvious. I think it's worth thinking about something a little more complicated. You may imagine that nums at -1 equals nums at n equals negative infinity. In other words, an element is always considered to be strictly greater than a neighbor that is outside of the array. I guess could you still just binary search anyway? If two numbers are... Let me think about this. This is interesting. So if you have some array, like this one, and you have your left and right pointer, I feel like you would want to just compare L and R directly. Although I guess like sort of the point of a binary search is to take a middle point and do something with that. I don't think this is like a ternary search. I don't think that has a place here. Ternary searches to me are like for optimizing. And if you're trying to use a ternary search across an array, you almost always want to be using a binary search. But maybe I'm wrong. I don't know. Find a peak element. Strictly greater than its neighbors. I assume that means its immediate neighbors. So here 2 would work. 0, 1, 2, 3, 4, 5. Well, 5 works, and that's the maximum. That works. Is it talking about what happens if you had like 1, 2, 1, 2, something like that? And then if we just said return 3, is this valid? Well, actually, that still does not really prove my point. I guess I'm thinking, what if we had 1, 3, 1, 2? Does it have to be the global maximum or just the local maximum? Okay, it can just be a local maximum. Okay, I'm gonna go to the bathroom real quick and think about this. Okay. So I think I had a half of an epiphany on my throne. So I feel like if like binary searching definitely makes sense here. I feel like if you have these 2 points, let's say you don't even look at the middle point, you just look at 1 and 4. If you start at the edges, you know that these are greater than the void because that's specified in the problem. It's greater than anything that's outside of the array. So between these 2 points, you look at the one that's greater, and then you move the other one halfway to there. So then this would be, let's say this turns to 5 or something. Yeah, I think it would completely turn to 3, but whatever. Let's say right is moved to the middle point that's 5. Then you would say which one of these is greater? The 5 is. So then the 4 moves into the middle of that. And then I feel like what you're saying is every step of the way, you'll always, well, no, because what if there was like 5, 6, 8, 4, and then you went, oh, 5 is greater than 4, so move the 4 to a 6. And then you would say 6 is greater than 5, so now we've found our answer, I guess. Like, I actually don't think that would work. But I feel like it comes down to this like invariant across this while loop of L and R. It's like, they have to be like greater than each side. I guess what you would do is you would look at the middle and you would say, whatever this is, I don't even care what this is. Is it a local maximum? If it is, return it because you don't have to do anything else. So like if it landed directly on the 8 somehow, then you would just instantly return that. If it's not a local maximum, look at either side and be like, is this increasing or decreasing? Because it's always going to be like something lower, it, and then something higher, or something higher, it, and then something lower. And then depending on which one it is, like this is increasing. So you would move the left pointer to that point, to the middle pointer. And then you would find another middle pointer and say, and it's increasing again. So move the left pointer there. And then you would find the middle pointer and you would say it's a local maximums. But even if you didn't do that, I think you could just say like, is nums at I greater than nums at I minus 1? Yes. So then move the right pointer there. And then you would have your answer. That makes sense. So you're not really binary searching because you are skipping a bunch of stuff and it's not monotonic, but you're kind of doing this like greedy taking. I don't know how I would describe this, but I think every step of the way, the invariant that you're maintaining is that like every single point is going to be greater than like your L and your R. L is going to be greater than everything to the left and R is going to be greater than everything to the right. So I guess you do sort of have monotonicity. Or not even greater than everything, just greater than its immediate left neighbor and greater than its immediate right neighbor. Okay, so you say while R minus L is greater than 1, M equals L plus R minus L over 2. People do it this way to avoid integer overflow, but it doesn't really matter in Python. And then if nums at M is greater than nums at M minus 1, is this ever 0? No, it's never 0 because at the point where it was 0, R was 1 and L was 0. That's the only way M could ever be 0. But at that point, this loop wouldn't have gone through. So if it's greater than its immediate left neighbor, then L equals M, else R equals M. Okay, and then in the end, I think you would just return L. I feel like there's some issues with this, but because what happens if like the greatest thing is at the very end, like is R? Now that should be fine too, because L will just converge up to R minus 1. Okay. Boom, there it is. It's kind of an interesting one. I wonder if my previous solution was just linear. It's definitely longer. Merge intervals. I feel like this is a really good problem to know. No, never mind. This is a pretty good problem to know. Return an array of non-overlapping intervals that cover all the intervals in the input. I don't think is it sorted? I don't know. I guess intervals.sort. So now it's sorted by start time and then end time. Okay. And then I guess we'll say the current time is equal to intervals 0 at 0. And then we'll say for start and end in intervals. Then we're going to have some sort of res. Do something with res, and then in the end return res. So what we say is like look through every single start and end time in the interval. If the current start time is greater than t, then we know that our current interval has ended. So I guess like res at -1 dot append t. Because res is going to be like a list of lists if I'm not mistaken. And then res dot append that. Okay. So we're sort of saying like end the previous interval, start the current interval. Like start a new interval. Or else t equals e. I think we want to say t equals max t and e. Because you could have a situation where like an interval starts at a later point and ends at an earlier point, and you don't want to like go backward. You don't want to like limit yourself. And then in the end, we just need to actually, I think, say just res at -1 dot append t. I think there's nothing too complicated there. 15, 15, interesting. Oh, I think it's because we don't actually need that to be an else. We just always take the maximum. All right, that checks out to me. So this is kind of like, this is a really, really, really preliminary version of sweep line. It's like the name of this algorithm. And it's kind of, I feel like sweep line is one of those things that is used in actual coding practices. Because intervals are a pretty common thing like in the real world. But it was, if I'm not mistaken, the sweep line algorithm was developed specifically for competitive coding. Like some smart competitive coder came up with it. That's the same for Mo's algorithm. I guess Mo came up with it. And it's one of those interesting algorithms that was developed for competitive coding, but it was actually started to be used in the real world as well. A lot of things were developed for competitive coding and not used in the real world. But I don't think the point is to like learn a body of knowledge that you're going to use. I think it's actually it's more to like just exercise your mind. It's like if you work on a farm, you're never going to see a dumbbell lying around the barn, but lifting dumbbells helps. Given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. Yeah, I could see the pitfall here that people would fall into being like, oh, you just always go to like node dot right. So you go from 1 to 3 to 4. But you could imagine like if node 5 here had a child, like if 5 dot left was 6, then you would want 1, 3, 4, 6, but that kind of shoots that down. I imagine a lot of people get caught up in that and then they get stuck because that's like solidified as their only option. But really, I think you just want to do a level order traversal. So you do a level order traversal, you parse every level, and then you just like add the last node in the level. So res equals that, q equals dec with root in it, while q, c equals length of q. This is my level order traversal kind of template I always write out. For blank in range c, so do something with the current level. And then I guess here we'll say res dot append q at -1 dot val, and then return res. So then for every node in every level, we just want to say if node node equals q dot pop left, if node dot left, q dot append left, node dot left, and then do the same for node dot right. None type has no attribute val. Oh, it's if it's literally just empty. So I guess if not root, return res. 1225. Okay. 1325. All right, something's definitely wonky here. Print q. Print x dot val for x and q. So 1, 3, 2, 2, 5. That's really whack. That's not what it's supposed to be. I'm guessing, okay, this is what it is. Yeah. I think in my mind, and probably in a lot of people's minds, you use push and pop for a stack, and append left is like a queue thing. I just made kind of a newbie mistake right there. It's like, really what matters is that if you're appending, it's to the opposite side that you're popping from, then it's a queue, and if it's the same side, then it's a stack. And if both of them are append left and pop left, then it's still a stack, even if it feels queuey because you're using the left side. Okay, 3 sum. All right, find 3 numbers that add to 0. Let's see. So 2 sum, you could just have like a rolling hash map of what you've seen. You check the current number against that. You check like the negative current number. The 3 sum, I'm guessing the constraints are, okay, 3000. I mean, this is like a tried and true. The fact that I don't have this literally memorized is a little bit embarrassing. I guess I feel like there's multiple ways to do 2 sum, and you just combine 2 of them to do 3 sum. So you say, sort it. For every, like one approach is you say for every I and every J, check. Does that work? Like if I can get it down to O of n squared, I don't actually know if that's good enough because n can be 3000. But this also feels like an old enough question that 3000 is okay. Like this is question 15. So this is like an ancient question. And I feel like modern questions 3000, they're almost screaming at you, do not do this in O of n squared. Because that's like 10 to the 7th, but I assume that's probably okay here. So nums.sort. And then you could just say for every node, parse through linearly. I don't even think you really would have to sort it if you're doing this like truly in O of n squared. I think you just say like for I in range length nums, range n, because I'm sure gonna write that a lot. You just say like, okay, try taking this as the constant. Now you're looking for 2 things after this that sum to this. So then do the normal approach. I don't know. I don't know if that'll pass, but this is about the most like bare bones thing I can think of that's O of n squared. Okay, so scene is a dictionary. What we're looking for is nums at I. We're saying like find 2 numbers that add up to negative nums at I guess. guess we want to say seen is a counter and seen at 0 equals 1. Because again, no, that's not the part of this. Okay, and then for j in range I plus 1 n, seen dot add nums of j. And then we're saying we want two numbers with a difference of x. So if something in seen, oh wait, what are we outputting? Return all the triplets. Okay, that doesn't really change anything. That's just like res is this, and then in the end we're just returning res. Okay, so seen shouldn't be a counter because we're not counting like the number of occurrences. Seen is actually going to be a default dict of lists. So we're saying like for every number, at what index have you seen that? And then here we just say like res.append. Actually, there's probably a really nice way I can write this. So y equals nums at j. And then you're looking for what z is going to be is nums at is going to be x minus let's see, if z is x minus y, you're saying x plus y plus x minus y. Let's see, if x was 0, then you want to find negative y. So negative x minus y. Negative x minus y. So we're looking for negative x minus y. So we'll say for k in seen at z, so we're sort of saying like this would be the number that given x and y would add everything up to 0. For k in seen at z, so for all the indices that actually contain that, res.append ijk. Okay. Int object k in seen at z. Oh, so you know why dot append j. 021 043. Oh, it wants us to add x, y, and z. Okay. And I guess it doesn't want repeats. I see. So it wants all of the distinct triplets. A really quick solution would just be to make res be a set and add them. But that's going to add like a hashing overhead. And I think instead of doing that, you could just say nums.sort. And then say if, yeah. Okay, so now we don't ever want to have a copy. So I guess right in this stage, we would say if x equals y equals x, does that matter? When do we want to skip? I think we only ever want to skip when, whatever. I'll just make this a set and hope that it passes. It doesn't really matter. Okay, and then in the end, we add a list of res. Hashable type. Do that. Okay, there's one more thing we have to do, and this is actually quickly getting. Let's see. Yeah. Okay. Still need to sort it so that everything's in the right order. I have no real confidence that this will pass. If this was a modern problem, this would be insulting, but fingers crossed, I guess. Yeah. Yeah, they got me good there. So let's see here. I think you can like optimize a bit. I think the first thing you can do is you can limit the occurrence of any single number. Oh wait, yeah, okay, this totally actually makes this. Oh, never mind. But you can limit the occurrence of any single number to 2 times. Because if it happens more than twice, you don't ever want to look at that. That seems pretty hacky, though. Is there a way to get rid of the set? Because that seems like the thing to do here. I don't think you ever want to have x be the same twice. Like if x was already 0, you never want to look for another 2 numbers that are adding to 0. And I think that's probably true for y as well. Yeah. Okay, yeah. So I'll say like if I and x equals nums at I minus 1, continue. That's one optimization. And then here I think we can say the same thing. That's like if j is greater than I plus 1. So if we've covered at least one thing and y is equal to nums at j minus 1, then continue there as well. So when I is 0, this is fine. Oh, I guess you have to add in the initial. So maybe that's I plus 2. So you're saying j is I plus 1, and then j is I plus 2. Yeah, that's okay. Because when j is equal to I plus 1, this will never go through because nothing's been added to scene. Okay, I want to get this TLE. Cool, so now that passes really quickly. I think now res also doesn't need to be a set. I think res can be a list, which should even increase it more. Okay, cool. All right, fuck it. It's a set then. mean, screw it. -220. Oh man, this is all over the place. -211. If j is greater. Oh, I know. Right here, when I say this, that works for I because it's sorted, but for j, that doesn't work. I think I just say if j in scene. No, I don't even think I need that. I think that just doesn't even need to be there. I'm trying to work around this, like, what if this were a list kind of logic, because I think that's kind of important. All right, whatever. Ah, that's a rare thing to see in Python. You see that a lot in C++. Okay, so I think it really wants you to use a list, which means I actually do have to think a little harder about the logic of like when something is repeating. So if I just have a list here, let me see. Well, for k in scene at z, this I think can be a set. Because this was back when I was like, oh, we have to keep track of the indices, but we don't. We just have to keep track of the elements. So why is that? If z in scene, then do that. Okay, and then scene is now a set. So now there's not going to be some huge list of the exact same number over and over again. I'm gonna see if this works as a list. Okay, so what does this do? This adds a bunch of zeros. This is actually really useful. So that means that this is only happening once. X is only 0 a single time. And then Y and Z are 0 a bunch of times. So I think I can say something like, if Y in scene, we've already seen this. So just continue. You already checked this. But the only exception is if it plus itself works. So if Y plus Y equals X, then also append that, or else continue. Interesting. So X is 0. Y is 0 a bunch of times. The first time this doesn't go through. Okay, you add Y. Oh, The problem is that it's just going through this loop over and over again. Okay, the first time that it's not seen, this is what you could do. Okay, if it's seen, you continue. You don't want to bother. If Z in seen, or J is less than n minus 1, and nums at J plus 1 equals Z. Is this really what I want to do, or is this really ugly? Well, looks like it works, so I'm just going to try and run it again. It's the specific exception for if x is equal to y times 2, but I think this kind of covers it. It's just pretty ugly. Okay, convert binary tree to doubly linked, sorted doubly linked list. Binary search tree. Okay, that's not bad at all. So you could say something like def DFS node, and then x equals DFS of root, while how do you want to do this? Every single time that you call DFS, yeah, I guess you just say return DFS of root at 0. And what DFS is going to return is the start and the end. And actually, we need to say res equals this. And then res at 0 dot prev equals res at -1. Res at -1 dot next equals res at 0. Return res at 0. I assume they want prev and next. I don't really know. Or oh, left and right. So dot left dot right. Okay. I'll convert it in place. Okay, yeah, no, it's still like the same. I think this still is just fine. It's going to return the lowest and largest nodes. So we'll say L equals DFS of node dot left, R equals DFS of node dot right. So then these are going to be assumed to be doubly linked lists where there's R is like a list that contains the head and tail node. So then we'll say node dot right equals R0. Node dot left equals L1. Return L0 R1. So the rightmost node of the right doubly linked list, the leftmost node of the left doubly linked list. And then we also need to say R0 dot left equals node, L at 1 dot right equals node. I think this isn't quite complete though, because how do you handle null values? You have to say something that's like if not node. I guess just return none, none. Yeah. And then you say, okay, yeah. If R, do this. This is just going to be return none, like you didn't find anything. If L, do this. And then it's going to be L0 if L else node, R1 if R else node. Classic. If not root, return root. Okay. And they always get you with those. What if I gave you null? Return true if it's a valid palindrome. Um, I think we can say, whatever. Let's say S equals filter, S. And then what we're looking for is lambda C, C in ASCII lowercase. Or no, C in ASCII. I think ASCII includes lowercase and uppercase. And then return that, but everything's lowercase. Oh wait, this is not even what it's asking for. Built-in function's not iterable. ASCII letters is what I was looking for, but now I'm more interested in ASCII because that might be faster. No, that's not what I want. All right, looks good. Cool. Oh, I guess we oh, and includes numbers. Okay, that's frustrating. Cool. So this beats most submissions, or like its average, despite having this weird, like you're searching for every character in the loop, because this is only 36 characters long, this string. So you're doing like 36 operations for every character, which is still linear. Okay, diameter of binary tree. I feel like this was the daily a couple days ago. I think literally yesterday or today. The length of the longest path between any two nodes in the tree. So people were actually just asking about this question. Because I think everybody's impulse is to use a global variable. You're like MSF equals 0, return MSF, and then you're going to do some sort of recursive function where you say def DFS node, DFS root, and then what DFS is going to do is it's going to like return the longest path up to the given node. So we'll say like path equals 0. Not node, return, I guess, -1. So then we'll say path equals max, DFS node dot left, DFS node dot right, +1, return path. Yeah. So now we have a sort of way to recursively find the longest path from a given node to any one of its most distant leaf nodes. But really what we want to do now is say something like L is this, and R is this, okay? And then return max L +1. Okay, so that's translated that, and then also you want to say something like global MSF equals max MSF L plus R plus 2. So you're kind of saying like, oops, okay, it hates that. So we'll just say self.msf, sort of get around that. And this is exactly, I think, where this runs into issues. Like it works and it's great, but I think a lot of people are like, I don't know how I feel about a class having a state that's just the maximum. That feels weird. Can you do it without this like meta global variable that you've used? And you totally can. It's pretty simple actually. You just sort of have two outputs for your node. Instead of saying like return the longest path, you say return the longest path and also just this again. So now we'll say like MSF equals, so okay, so I should explain this a little bit. So now DFS is taking in the node and it's now returning two things. It's going to return the longest path. The longest path up to this node, and also like the longest path between any two nodes in this subtree. So it's sort of like you're changing MSF and you're turning it into this local variable and just updating it constantly. And like the way that you're keeping track of it is by submitting it as a parameter, or not even submitting it as a parameter. You're just like returning it multiple times rather than setting a global to it multiple times. MSF equals max. L at 1, R at 1, 0, L at 0. Okay. And then now we don't have this like weird void function anymore that's changing global variable. We're just saying, okay, return DFS at root. That's going to give us the longest path from the root to any given leaf node, and also the answer that we're looking for. So return DFS at root at 1. Oops. Wait, no, that was fine. Oh. Int object is not subscriptable. Cool. Oh, right here. You want to say -1, and then the maximum can just be like 0. Int and list. Oh, right here we want to say L at 0, R at 0. Greater than is not supported between int and list. Interesting. So this is an int, and this is an int. So it must be referring to this max. Oh. Okay, well, that's a dumb typo, I guess. I guess using a global variable would be a little bit faster, because here you have to pass through, every single function is now returning two things. So that's sort of an extra like throughput of data throughout your recursive algorithm. I'll try to quickly make it 30 questions and then call it. I think that's what I'm going to do. LRU Cache. This one's like a classic. And an interesting one too. So least recently used. Yeah. So there's like multiple pieces here. So initialize an LRU cache with a capacity. Turn the value of the key if it exists, otherwise -1. Update the value of the key if the key exists. I think also get updates the usage. It doesn't say that here, but that's like important. Update the value of the key if the key exists, otherwise add the key value pair to the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key. So what we kind of want is like a doubly linked list. We want like two structures. On one side, we want, let's say, doubly linked list. And this is going to keep track of like what's been used and what hasn't been used. So like in order of frequency. And then on the other side, we want a way to say like, given a key, find the node in the linked list. So this is gonna like eat a number and then go there. Yeah. I have to like clear my mind of the LFU cache, which is sort of the next level on this one, which is like pretty complicated. And this one, again, this one almost is like a matter of memorization, I feel like. But it is interesting to like work through. So we have a linked list. What happens is in the init, we just initialize them. That's easy. With a get, you say, see if the node is in here. If it's not, return -1. The node is in a node. Sorry, if the node associated with the key does exist, move that to the top. Get rid of where it was. And then return it, I guess. For put, we say, okay, put the node in here at the top. And then if the linked list is too long, then pop from the back. So that all makes sense to me. I'm wondering if this can be done with a deck. The put operation certainly can be. Because with put, you're just like append it and then pop left if it's too long. So that's pretty simple. As far as the get operation, I don't know, like, I could try to parse through this and see put, okay, do you get 1? Put 3. Okay, yeah. So get does reset. If you try and get something, it counts as a use, because right here you add a 1, you add a 2, then you access the 1, and then you add a 3, and it would have evicted the 1 if getting didn't matter. And that matters because that means like you're gonna have to move something from the middle up to the top. So I don't think, well, no, you totally could use a deck, I feel like. Because it's O of 1, to move anything from the middle to the top, you would just say like node.next.prev equals node.prev, node.prev.next equals node.next. And then you would say, okay, and now add the node to the head. But if you used a deck, I think what you could do is you could just say like, mark this node as not anything anymore. And if you see this at the top of the stack, just like remove it. Yeah. That's pretty, no, that's so sloppy. I'm gonna do it with like a linked list. That makes a lot more sense. Class list node. Self val. And I guess this will have just the value. What do you have in here? You say, it needs the value and the key. Because if the node is popped from the end, you need a way to look back in the dictionary and remove the key from the dictionary to count it as not like existing anymore. Self.val equals val, self.key equals key. Okay, I think that's all we really need there. Okay, so for init, we'll say head equals list node. List node. Okay. And these are going to be, the head and the tail is going to be like the, well, we don't really need a tail. The head is going to be like the sentinel. In fact, I think I'm going to call this like self.sent. Yeah. Yeah, okay. Yeah, okay. And then this is gonna be doubly linked list, so we'll say self dot next equals none, self dot prev equals none. Okay, so for get, that one's the more complicated one. I'll send it a dictionary. So self dot dict equals hash map. For get, that's the more complicated one, so we'll save it. For put, we say if self dot, I'm gonna actually just have an auxiliary like def update self node, I guess. Like given a node, update it to be at the top. Yeah. I guess we also need like a counter. To be like, how many things do we currently have? I think I'm going to say self dot cap equals capacity. So if key in self dot dict, then you do something, or else then you have to add it. So you say self dot dict key equals list node value key. Okay. And then I think I can just straight up add this. So like self.sent.next equals node. Node.prev equals self.sent. Sentinel being like the head. And then we also want to say node.next equals sent.next. Oh, what am I doing? Whatever, I'll just stick with sent. No, I'll say sent equals self.sent. Losing my marbles here, I guess. Node.prev is sent. Sent.next is node. I think we also have to say if this is the first thing that's been included, if n is equal to 0, or if I think I'll say if because sent is going to wrap around, so sent.next is going to be the first thing and sent.prev is going to be the last thing. So if you add the initial node, then you need to also say sent.prev equals node. So if sent.prev is sent, sent.prev equals node, node.next. No, I don't even think you need to have this. Yeah, okay, that was the last thing I'm missing. So node.next equals sent.next. Node.next.prev equals node. So you're saying set the next thing's previous node to be this. Set node's next node to be that. Okay, you just need these 4 operations. That's all you need. That's set up. Update is going to look very similar. In fact, I think I'm just going to say node equals self.dictate. Okay, and then here we want to remove it. So we'll say node.next.prev equals node.prev. Node.prev.next equals node.next. Okay, and this is the really nice thing about having a sentinel node in your doubly linked list is you don't have to have a bunch of if statements about what's what is none and what isn't none. And then I think this is going to be the update logic. So right here, I'll just say like update means insert it at the top of the doubly linked list. So either make the node, or if it already exists, remove it from wherever it is. Okay. That one makes sense. Yeah, okay. Oh, and then actually the final thing that needs to happen here is right here, we say self.cap minus equals 1 if self.cap is less than 0. Then you have to remove the final node. So you say marked equals sent dot prev self dot dict dot pop marked dot key. So get rid of the key, pretend it doesn't exist anymore. And now sent dot prev equals sent dot prev dot prev. It's oh, there's one more thing you have to do. You have to say marked. Well, I'll say sent dot prev equals marked dot prev marked dot prev dot next equals sent. Okay. That looks good. And then get is actually almost exactly the same. Key in self.dict, do something else, return -1. So we say node equals self.dict key. Remove it from wherever it is and update it. Uh-oh. Node is none. That's a pretty bad sign. Oh, I know what it is. It's that sent should be sent.next is sent. Sent.prev is sent. When we start out, everything is just like the circular empty array. I feel like you could do this in a buffer ring and it would be better. All right, I'm just going to run it and kind of hope that it works. Whoa. Put a 2, 2, 2, get a 2, put a 1, put 4. Oh, I never actually update the value if there's an existing value. So if it already exists, then say node. There we go. I forgot to actually update the value. That's funny. Whew. Okay, move zeros, k closest points, top frequent something, some route to leaves. Okay, those don't sound too bad. Give an integer array nums, move all the zeros to the end of it while maintaining the relative order of the non-zero elements. All right, I think I'm gonna just like nums. This is like I'm gonna hard write something in. So straight up nums, now the values of nums are gonna be equal to let's see, it's gonna be cool. So this is like pretty hacky. This is clearly not what they want you to do. They clearly want you to like keep 2 pointers and do some like at the end of the array decrement j. And this is O of n space, whereas this is O of 1 space, but whatever. I think understanding deep copying of lists in Python is probably a little flashier than like fiddling around with pointers. Given an array of points, return the k closest points to the origin. Okay, so this is pretty much exactly the same as kth largest, but now you're just using like Euclidean distance. So dist equals lambda x comma y. Math.square root of x squared plus y squared. And then we'll say something like h is this for point in points, heap push h, and then dist from that point to the origin. Star here means like take everything out of this iterable and submit that as here the like thing that you want dist to operate on. So like dist is taking in x and y. If I just said dist of point, point contains the x and the y we care about, but then I'd be submitting a list. If I have the star, I'm saying like submit the contents of this list, which is two things. So if point was like in 3 dimensions, like 1, 3, 3, it would throw an error. But that's the flag. And then we want the k closest points. So I think we want this to be negative. So it's going to sort of like, if you pop from h, it's going to pop the largest thing. Okay. And then say length of h is greater than k. Heap pop h. Return. You can return the answer in any order. So x1 for x and h. Cool. And here this is the same like min heap max heap trick where this is slightly faster. This is n log k as opposed to n log n. Okay, top k frequent elements. This seems pretty similar. So I guess c equals counter nums. H is this for key and value in C. Heap push H. And then you want to say the value is the count and the key is like the thing that you need to care about. The value is the flag and the key is the value, which is kind of confusing. Return the answer in any order. So again, return x1 for x in h. 1, 1, 1, 2, 2, 3. I'm saying 3, 1, 2. X is greater than k. Oh, it's because I'm using k as like the name for this. So I'll just say v and x. It's like x is the element. Cool, okay. Okay, sum root to leaf. The last one. You're given the root of a binary tree containing 0 to 9. Return the total sum of all root to leaf numbers. Okay. So I guess I want to have something that's like def DFS node. And then what this is going to return is like returns the list of all numbers. I can't imagine the amount of nodes here can be very large. Okay, 1,000. And the depth does not exceed 10. I think that's actually the most important thing. Is it? Okay, let me think about this. Because I'm thinking, like... No, I'm overthinking this. Yeah, I think I'm overthinking this. I was going to say, like, you could do some bottom-up thing where you, like, keep a track of all the lists of the numbers, but I think when you go top-down, you just say, like, what node are you looking at, and what's your current prefix of numbers that you've got. And then here I will just use a global variable because it seems really kind of simple. So we'll say eventually DFS root and nothing, return res. So here the first thing we want to do, I guess we say if not node, return pref.append node.val. And I'll actually just go ahead and say string node.val. If not node.left and not node.right. Okay, if this is a leaf node, then we'll say self.res plus equals the integer of all of the joined numbers. Oops. Yeah, I said 115. Oh, because you actually have to pop it off at the end. Boom. Oh man, well there's 30 Facebook questions. What was my timing on these? That's really what I care about. $248. So if I round up to 3 hours for 30 questions, what is that? After all those string manipulation and bit manipulation questions. Oh man. I feel like you've probably seen a lot of these too, IO. What is that? 248. So it's like 120, 168. So 168 over 30. All right, yeah, that's like under 6 minutes a question. No, I'm just streaming on YouTube. Twitch is I don't know why I'm not streaming on Twitch. I like YouTube more. My favorite color is red, so. I guess I'll do like 31 through 60 at another point. I think I am just gonna like start submitting to random places. The main reason is it feels like not disingenuous, but it feels weird giving so many mock interviews when I'm like, I don't really know. Yeah, I could probably dual stream. I think it's because like YouTube, I don't know. I like to think this is a little artifact, you know? Like I like to think someone could just pull this up and be like, what are all the meta questions for 2024? But for Twitch, it feels like this, like if I was really good at League of Legends or something. Like if I was gonna stream on Twitch, I'd want to have like copyright free trance music playing or something like that. I have a couple minutes before I think I'm gonna take my dog out. Are there any like algorithm concepts you're curious about right now? Yeah, exactly. I wonder if OpenAI is hiring right now. I feel like I've seen those charts recently that pretty much are like Meta's hiring, everywhere else is starting to hire very slightly. Q4 last contest. Yeah, I don't know how much I'm going to be able to speak to that one. I lucked out that I skipped that contest because that problem, I think it's the hardest problem. Well, I guess 179, this problem was supposedly really hard. But someone was saying, I think like whatever the Chinese version of this guy's GitHub like problem rankings, there's like another Chinese GitHub dude that has his own or their own, and I guess they update it more frequently, and supposedly that problem is the hardest problem LeetCode's ever had. I feel like OpenAI's gotta be on the up and up. I mean, like obviously, but just in terms of sheer hiring, I feel like if someone were looking for any place to apply to right now, it would be OpenAI, and I guess like Snowflake, but that's supposedly really hard to get into. I know, I just didn't feel like it. I was like, because I've been doing so well on these contests. This is a classic me thing. I'm like, okay, so I've been doing really well, and so the right thing to do is to stop and live in fear of my score going down. But also, I mean, at least for me, I'm in a spot where I get so fixated on this, and this is great. It's really productive, but I think it's kind of easy where like to draw this false sense of productivity from something that's like quickly becoming just a video game. I don't think that's true for most people, but New Jersey. I was thinking about, I don't, some people tell me I would really like New York. Some people tell me I would really hate it. Q3, yeah, Q3 was interesting too. I knew what to do for Q4, but the implementation, I spent a little bit of time on the virtual afterwards. I got tripped up on Q3 because I like I overread the problem. Q4 was like a whole thing. So for Q3, what is it? Just like a binary search? You binary search and you're like, can I do everything in this time? Can I do everything in this time? That one kind of made sense to me. Q4 was also a binary search. But what was I doing here? This is going to take me a minute to. I think the thing to recognize is that you never want to decrement anything by one, because you could always just set it to be 0. So the question really becomes like, well, okay, let me rephrase that. You want to only decrement things to 1 that you don't have access to. So let's say you're trying to do everything in like 5 seconds. That's a bad example. Let's say you're trying to do everything in 2 seconds. You don't have access to this 3rd index, so you have to decrement that 3rd index by 3. Like this is going to take you 3 seconds no matter what. So I think the thing to recognize is like you always spend n seconds marking everything because you have to actually spend a second to mark it. So that's n seconds out of the way always, no matter what. You have to, if you don't have access to certain indices, like here you don't have access to index 3, 1 index, you always have to decrement that 1 by 1. Everything else you can decrement to 0 instantly. So it sort of becomes like, how many zeros do you have access to? Like how do I put it? Like here, for example, you don't have to do anything with these. You don't have to decrement them. You don't have to set them to 0. So it's like at every step of the way, at every second, do you have anything you can like mark that's 0? Otherwise, set something to 0. So it's an interesting problem. I think it's like a combination of, you know, binary search, but then really it becomes about the predicate, and like, I guess it's greedy. I guess greedy is the right way to put it. I don't honestly like. I mean, 36 accepted for a modern contest is ridiculously small. I think the reason why the acceptance was so low was just there was so much to keep track of. Like you have 4 different options, even if you say one of them, like for example, the logic I just went through where it's like, well, the only time you'd ever decrement anything by 1 instead of straight up setting it to 0 is if you don't have access in change indices to that element. It's like, okay, that logic's fine. That's like potentially questionable, but I think it's right. And like now you've shaved off one of these 4 options. You still have 3 other options. And like if the amount of effort and self-questioning is going to be the same for these, it's like that's so much to keep track of. And then when you reach a point and you get some wrong answer or TLE, it's like then you have to think, where was I off? So it's sort of like those basic calculator questions where there's so much going on that feels a lot about the implementation. That's how this felt to me, except instead of like with a calculator question, it's like a lot going on in terms of lines of code. Here, it's like there's a lot going on conceptually, which is cool. Yeah, I'm going to take my dog out in a couple minutes, I think. I thought about doing a like speed run of the blind 75. I think that'd be fun. Getting TLE on this. This is rough, yeah. And they don't make these like 5,000 is a really awkward number for these contests because that means you can't do O of n squared really. I guess what would this be? So it's O of n, O of log n for this, and then at least n for this. I think I heard some people were using a q. So that's n log n. So it would be n log n, and log of 5,000 is like 12. So that would be 100 times 1,000 times 4, I guess, and change. So that would pass easily, I guess. I guess that logic makes sense. N log n. Sweet. Yeah, I think I'm gonna finish up the meta questions, and then I'll do the blind 75. I think also in terms of frequency, the less frequent you go, as far as the top frequencies, the more hards show up, which hopefully is more interesting than just like ranged sum of BST or whatever. Yeah, that was a fun stream. Thanks for tuning in. I'll talk to you guys later.